Hello everyone. In this section, we will talk about some important probability distributions used in quality engineering. The learning objectives for this session are to discuss the nature of binomial and Poisson probability distributions for discrete random variables, the context in which these distributions are useful, and their important characteristics. We will also calculate the probability of a given event using binomial and Poisson probability distributions, and we will describe the normal distribution for continuous random variables. Now, in the last session, we defined the generic probability distribution functions for describing random variables. We talked about the probability mass function, or PMF, for describing discrete random variables, and the probability density function, or PDF, for describing continuous random variables. These mathematical functions have certain properties, and many different PMFs and PDFs have been proposed to describe random variables encountered in various different situations. Now we're going to go into more detail and discuss three probability distributions that are most useful for describing random variables encountered in quality engineering. The binomial and Poisson distributions are probability distributions both for discrete random variables, and the normal distribution describes continuous random variables. But before we start, we need to review slightly our combinatorics. Just one point. The number of combinations of n distinct objects taken r at a time is written as shown here. It's a number of n distinct objects taken r at a time. And this is given, it's a mathematical function, given by n factorial over r factorial over n minus r factorial, where r is less than or equal to n. So you can imagine this, you have three different balls, for example, and you want to take, so n equals 3, you want to take 2 at a time, you can take those two, or you can take these two, or you can take these two, for example. N factorial is defined here. It's 1, it's equal to 1 for n equals 0. It's equal to 1 times 2 times 3 up until n for n is greater than or equal to 1. So now we're going to look at the binomial distribution. A random variable x is said to have the binomial distribution with parameters n and p if its probability distribution is given by the formula shown here, where the first term is the number of possible combinations of n distinct objects taken x at a time. The quantities n and p have to be specified in order to complete the description of the binomial distribution. And we use this notation bi and p to indicate that x has a binomial distribution with parameters, again, parameters n and p. Now, what does this mean? For the binomial distribution, x, our random variable, represents the number of successes in n independent trials, where p is the probability of a success and 1 minus p is the probability of a failure in one trial. This is called a Bernoulli trial after the Swiss mathematician Jacob Bernoulli. And what a Bernoulli trial is, it's a random experiment with exactly two possible outcomes, either a success or a failure, and in which the probability of success is the same every time the experiment is conducted. This means that our random variable x can take the values 0, so no successes, 1 success, 2, up until n, because when the trial is repeated n times, the number of successes could be 0, 1, 2, up until n. The binomial distribution has the parameter p, which is a probability of success, and this means that p has to be between 0 and 1. A high probability of success means that p is close to 1, and a low probability of success means that p then is close to 0. So let's go back to our game. Remember our coin flipping game that we played? If I say that the number of eagles is a success, so for me, success equals an eagle, because in that case, I got a euro from everyone. Then if I flip the coin, what is the probability of a success? So this is a perfect example of a Bernoulli random variable. X is going to be, as we said, the number of successes in n Bernoulli trials, independent trials. And for a fair coin, if I toss a coin, what's p? What's the probability? This is an eagle. And we know that p is going to be 0.5, which is equal, of course, to 50%. So 1 minus p then, which would be the probability that I get a number, is also going to be 0.5. That's for a fair coin. Now we tossed the coin 10 times. And we had how many eagles here? I won 9 times. So we want to understand what is the probability that we will have 9 successes if we have 10 independent Bernoulli trials with a probability of success of 0.05. So we can write that then here as 10 over 9 times p, which is 0.5 to the 9th power, times 1 minus p to the 10 minus 9, and this 10 over 9, that's 0.5 to the 9, 0.5 to the 1. If you calculate that out, you get 0.0098, or less than 1% that we get 9 eagles using a fair coin in 10 tosses. So you had every reason to complain when we played the game, and now you can see why. So what does this shape, though, of the binomial distribution look like? Remember, x is the number of successes in n independent trials. And here we have a picture generated by Professor Arghun Chen from National Taiwan University. You can see this is the binomial function for different values of n. The bars here are for n equals 80, and the dots here are for n equals 30. So what we can see here is, and as the number of trials increases, the distribution moves away from 0. You also notice that the distribution never goes below 0, and you also notice that they have a bell shape. They do have a bell shape. The other variable that he changed was we have for this distribution here, we have p equals 0.1, so 10% success of probability. And for this one, p equals 0.1. And for this one, we have p equals 0.2, and p equals 0.2. So you also see, as p increases, you also see a shift away from 0. So that's how the distribution looks. All right, examples. For example, the number of heads when a fair coin is tossed 10 times. Binomially distributed, 10 with p equals 0.5. The number of baskets a ball player makes in 12 free throws if her average is 0.4. Or, in terms of quality, say we're looking for the number of defectives in a sample of 20 taken from a large product batch having 2% defectives. Now, in this third example here, we talked about the number of successes. The P is the probability of a success. And in this case, we're looking for the number of defects. So we're defining the defect as a success. So to be a little careful, because obviously a defect is not a success. But for the binomial model, the P is then 0.02. Now, it's important to understand that in order to use the binomial model to represent the number of successes in n trials, every trial must be independent. Now, for example, when we toss the coin 10 times and we count the number of heads, the trials are obviously independent because the outcome from the first toss of the coin will not affect the outcome of the second, and so on and so forth. So that's a good example. For the basketball player making a free throw, it might be reasonable to assume that the trials are independent. They may not strictly be independent because maybe the basketball player gets tired. But the assumption of independence is necessary in order to use the binomial model in this case. So as long as she doesn't get tired. Now here, in the third example, we're talking about a production batch. So these are products that are produced together during the production, produced on the same machines at the same time. And this is called a production batch or production lot. And here, if we know we have in general 2% defectives, and we take one of them away, that will affect then the overall percentage. So the independence requirement will not be met if the sample is chosen from a small lot, as the individual picks, because they're made then without replacement, will not be independent. And as the lot size becomes large compared to the sample size, so lot size has to be large compared to the sample size, then we can assume independence, and we can basically assume if the sample, if the lot size is greater than or equal to, say, 30, fairly big number, and we take a small sample, then we can assume that the trials are independent and we can use the Bernoulli distribution. So just a note on that. Let's do an example. We have an example of 12 bolts picked from a production line and inspected. And if we know that our production produces on average 2% defective, what is the probability that our sample will have exactly one defective? So we have X is the number of defectives in a sample, and we have N equals 12, and we have P equals 0.02, the probability that we find a defective. So what we're interested, what's the probability that the sample will have exactly one defective? So P of X is going to be a combination of 12 over X times 0.02 to the X times 1 minus 0.02 to the 12 minus X, and we're interested in exactly one defect. So we have 12 over 1 times 0.02 to the 1 times 0.98 to the 11, and if we calculate that out, we get 0.192, or 19.2% chance that our sample will have exactly one defect. Last slide, the mean and the variance of a binomial variable can be calculated as we learned before. Don't forget, mu is the weighted average of the distribution, and the variance, sigma squared, is the squared deviation of the values of the variable from its mean, so it's a measure of dispersion or variability. And here, for the binomial distribution, the mean is simply equal to NP, and the standard deviation is equal to NP times 1 minus P. And these represent the long-run average and long-run standard deviation of the binomial random variable. Okay, so we're going to now look at the Poisson distribution. This is given by this function here, this probability mass function here. It takes values from 0 to infinity, and that's often used as a clue for recognizing Poisson variables. The possible values are countable, it's discrete, and it could be anywhere from 0 to a very large number. And we write PO lambda to indicate that X has a Poisson distribution. Now, it has one characteristic variable, and this is lambda. So let's look at what this means. How do you recognize a Poisson variable? The variable is countable, as we just said, takes only positive values from 0 to infinity. Examples could be the number of knots per sheet of plywood, the number of blemishes per fabricated shirt, the number of pinholes, maybe in a sheet of galvanized iron, the number of accidents per month in a factory, for example. So each can be counted and take values from 0 to infinity. Now this may sound a little bit like your binomial variable where you're looking, for example, for defects. So the way you can tell these apart, if you have a mean or an average probability of an event happening per unit time, per page, per mile, that an average value of an event happening per unit. This could be time, this could be miles, etc., etc., etc. Then you can be, and if then you're asked to calculate the probability of n events, so you have the average value of event, and you're asked to calculate the probability of n events happening in a given period of time, a number of pages, number of miles cycled, then you use the Poisson distribution with the characteristic lambda. But if on the other hand, if you have an exact probability of an event happening in the question, that is, and you're asked to calculate the probability of this event happening k out of n times, so a number of times out of n independent trials, that's your binomial. That's when you know the exact probability p, and you're asked how many times that will happen in n dependent trials. So the Poisson approaches a binomial as n approaches infinity and p approaches 0, and I put out here, we write PO lambda to indicate that X has a Poisson distribution. So what does the Poisson distribution look like? Here we have again from Professor Chan the Poisson distribution for different values. Here we have the distribution for lambda equal to 10. Here we have the distribution for lambda equal to 4. And here we have the distribution for lambda equal to 1. Just a note, these are discrete distributions, not a continuous distribution. So actually, these are actually also bars here, not a dotted line, indicating the probabilities at each specific value of the random variable, and the same for the lambda equal to 1. What we notice is that, again, this distribution, like the binomial, never goes smaller than 0. And as lambda gets bigger, you can see the sort of familiar bell-shaped function. Again, it's a discrete distribution, it's not continuous, but it is a bell shape, more symmetrical. As lambda gets bigger, Lambda larger, it's moving further away from 0 and becoming more symmetric. We can calculate the mean and the variance, the same as before, and here it's very easy. The mean and the variance for a Poisson distributed random variable is simply lambda. So again, the long run average or the long run mean of having an event occur. So that concludes the two main discrete distribution functions, probability mass functions, that are mostly used in quality engineering. We're going to do calculating Poisson probabilities. So calculating Poisson probabilities, here's an example. A typist makes on the average 3 mistakes per page. On average. Gives us already a hint that that's our lambda. What's the probability that the page he types for a typing test will have no more than 1 mistake? So let x equal the number of mistakes per page. Then x is going to be distributed according to the Poisson distribution with the characteristic parameter lambda equals, on average, 3 mistakes per page. The probability that there is no more than 1 mistake per page is going to be then equal to, well, first let's write out the equation. So we have the probability of x is equal to e to the minus lambda times lambda to x over x factorial. And so the probability that we have no more than 1 mistake per page is equal to the probability that x is less than or equal to 1, no more than 1 mistake, is equal to the probability of x equals 0 plus the probability of x equal to 1, which is going to be e to the minus 3 times 3 to the 0 over 0 factorial plus 3 to the 1 over 1 factorial. Just plugging in the x values there. And here then we get e to the minus 3 times 4, which is equal to 0.199, or 19.9% that we have no more than 1 mistake per page. Oops. So look back at those two examples. In the Bernoulli, we were looking for the number of events happening in end-independent trials, and here, given an average value of an event happening, we're then asked to calculate a certain probability. So, continuous distribution models. We have many of these. Common ones are the uniform distribution. This one is, for example, when you throw a dice. Well, that's discrete, but uniform distribution. For all different values of your random variable x, you have the same probability. You also have an exponential distribution, for example. This looks like this. For all values of your random variable, you get an exponential decrease in the probabilities. So those, like for example, this is very used in reliability, for example. What we're going to talk about in detail in this course is the most well-known probability distribution, the normal or Gaussian distribution. And we'll do that in the next section. We frequently come across normally distributed random variables in quality engineering because most measurements, such as the length or the diameter of the bolts, the strength of the wire, the weight of parcels, all of these are examples of measurements that can be expected to follow the normal distribution. Often we would know that a random variable or a population has the normal distribution and we often know that it has an average and a variance, a known average and a known variance. And we'll be interested in finding the proportion of the population that lies within a given interval or given limits. And this is a major part of quality engineering. So a random variable x is said to have the normal distribution if its probability density function is given by this very complicated equation. We have two quantities here. You can see a sigma there and the mean there. So we can write that n is normally distributed with two variables, mean and sigma, or sigma squared here, which are, of course, the mean and the variance of the distribution. And if we specify these two values, then the distribution of the normal variable x is completely described. The graph of the normal distribution looks like this. So it's asymptotic to the x-axis, which means it doesn't ever quite cross the x-axis. It's symmetric about a line which occurs at x equals mu. And the maximum here occurs at the mean. The maximum probability occurs at the mean. It's the most likely value. And we have 2 points of inflection which occur at a distance sigma from the mean on each side of the mean. And as we did in the last section, we can also show that using our normal function, the area under the curve is equal to 1. The weighted average of the population is the mean, and the sum of all values from the average squared weighted by the function is the variance. And as we said, these are the two parameters, the mean and the variance, that completely describe the distribution.